Okay, so last time we talked about the basics of Ballerina, things that were common between Ballerina and other programming languages. Today we're going to start talking about the features of Ballerina that are distinctive, that make it worthwhile. So as I said in part one, if part one was all there was, Ballerina wouldn't be very interesting. But the features we're describing in part two, they're not individually novel. We wouldn't want to, in fact, we try to avoid things that have never been, we're not an experimental language. So we're not trying to, if there were features that had never been tried out in a real language, we wouldn't want them. But it's a combination, I think, that's distinctive. So I think we need to set these features. I mean, we're not being distinctive just for the hell of it. We're trying to be distinctive for a reason. So I think it's important to understand the context for Ballerina. What are we trying to achieve? So we're doing application programming, not systems programming. You're not going to write an operating system in Ballerina. We're emphasizing small to medium-sized programs. If you're, got a million-line code base, probably Ballerina is not going to be for you, at least not until our compiler speeds up a little bit. Our primary focus is integration. So we're more about gluing other programs together. We're more mortar than bricks. We have some similarities with scripting language, but I wouldn't call Ballerina a scripting language. It's a little bit more, but you can think of languages as being on a spectrum from systems programming on one end to scripting languages on the other, with applications somewhere in the middle. And we're, I'd say, a little bit on the scripting side of applications. So we're a pragmatic language, not an experimental or a research language. The measure of success is, do we have users who are satisfied, not how many research papers have we published. And related to that is this is a language which is designed to be used in industry and business. And so things like reliability and maintainability are important. And another really fundamental design constraint is that we don't want to overburden programmers. This shouldn't be something that is usable only by the people who've been to Stanford and have graduated in computer science and spend their whole life with this one language. That's not the kind of language we are. We're just language that should be usable by people without a huge investment of effort. We're more, if you like, we're not trying to brave there's not supposed to be an exciting new path that is a completely different way of doing things and stretches your mind. It's supposed to make life easier for you. So it's more, if you want to compare programming languages, our Zen is not Haskell, for example. Nothing wrong with Haskell, it's a great language. It's more like TypeScript. We're trying to make things that leverage familiarity and be usable by ordinary mortals, usable as one of several programming languages. And another thing we're trying to do is be suitable. We're a language that has been designed for the cloud era. Today's programming is going to be today and for the next decade or two. Now this slide is full of gross generalizations, but if we compare the pre-cloud era, going back, the 70s or 80s when I learned to program, to how things are today, it's a very different world. In the traditional era, the main way you get access to data is you read and write files. You get things done by reading and writing files. In the cloud era, it's much more about consuming and providing network services. That is the normal way you get things done. And similarly, when you want to talk to other code in the pre-cloud era, what an API means, an API is a library API. It's code. It may be native code or JVM or .NET. It's code that you call via a code API. Whereas APIs in the cloud era, they are network APIs that work over HTTP, JSON, or gRPC or whatever. UIs in the pre-cloud era are libraries specific to an operating system, whether it's Win32 or OS X or Linux, KDE, GNOME, whatever. Whereas in the cloud, you're not doing any of that. You're talking with JavaScript clients. Concurrency. In the pre-cloud era, most application programs don't really need to deal with concurrency. It's an advanced feature. If you try to get the average programmer to deal with threads and locks and so on, they're going to fall on their face. Well, I would anyway. Whereas in the cloud, concurrency is pervasive. You can't get away from it, and you can't just, application programs need to deal with it. And if you look at what were programming languages designed for, C, C++, Java, C#, those were really for the I'm sure they wouldn't agree with that, but they are initially designed for the pre-cloud era and have been adapted to work with cloud. Whereas if you think of things that have been designed for the modern world, I'd say we have JavaScript was designed a while ago, but it still has a vital role to play on the UI, on the client side. And then we have Ballerina, of course, which is designed to be more on the application side. And then you have things like Go and Rust. Rust, again, it's not, I wouldn't say it was a competitor of Ballerina or Init nor Go. They're designed for different problem spaces. Rust is designed more as a systems programming language. Go is an application programming language, but it's more targeting I think it has a different sweet spot from Ballerina. So when we look at the distinctive features of Ballerina, I think that we'll see three main themes. One is network interaction, then dealing with data, the kind of data that you can pass over the network, and concurrency. So starting with network interaction, you've really got two things we're trying to do. We're trying to consume services and we're going to provide them. Whoops, what happened there? I pressed completely the wrong button. And now I have lost myself. Oops. Let's go back. Okay. So consuming services is relatively straightforward compared to providing them. The basic concept is that we have a client object. So it's an object, it's a special kind of object called a client object. And when you define it, you use the client keyword before the class keyword. And what's different about client objects is they have remote methods. And remote methods are methods that are used to interact with a remote service. Now, typically, if you're writing an application, you don't need to write these client classes. They are provided for you. They're either generic to a particular protocol, in which case they're going to be provided by a library module, or they're application specific, in which they're typically going to be generated from some flavor of IDL. And these remote methods, so from the application point of view, what you need, the only thing you're doing differently with client objects is that you're making calls to remote methods and calls to, let me see, let's do that. Okay, can you see something on the screen here? Yes, okay. See something on the screen? Okay. So here we have, instead of using a dot to call a method, we use arrow to call the remote method. And this allows Ballerina to provide you with a different view of a function, which shows the remote method calls, the interactions with remote services using a sequence diagram view. And we also have restrictions on where, in order to support this view, we also have restrictions on where remote method calls are allowed. You can't have them deeply nested in expressions. So that's pretty much all there is to remote client objects. That they're not very complicated, but this little distinguished thing, making them syntactically distinguishable, making them syntactically distinguished, enables a nicer view. So providing services is more involved and involves the interaction of three main things. We have service objects. Service objects are the counterpart of client objects, and service objects also have remote methods. And these remote methods are the methods that are remotely accessible. So a remote method of a service object is something that is called by a remote system. a remote method of a client object is something that calls the remote system. The way a service object gets called is by having it attached to a listener object. A listener object receives network input, and as a result of that network input, it makes calls to remote methods of service objects that have been attached to it. Now, for a listener to work, that needs to be registered with a module. So modules have a life cycle. They're not just a modularity vehicle. They also have a life cycle. They are initialized on program startup. Once the module has been initialized, the registered listeners will start up. And then when the program shuts down, the registered modules go through a shutdown. The registered listeners go through a shutdown process. So the first bit is how do you make a listener? Well, you have something called a listener declaration, which looks a little bit like a variable declaration, but it also has the effect of registering the listener with the module so that the module can manage it. And if new should return an error there, the HTTP listener can return that new can return an error. And if it does, then your module initialization will fail and you'll get an error at runtime. So I mentioned that we have this concept of a module lifecycle. All modules are, so you've got a number of, your program consists of multiple modules. All these modules are initialized at a program startup. And during module initialization, all of our modules listeners are registered. And module initialization is ordered so that when one module imports another module, then the importing module is initialized after the imported module. And once you've finished initialization, then main gets called. After main finishes, then if listeners have been registered, we start listening. The listening phase starts by calling start on each of the registered listeners. And then the listening phase ends when you do a Control-C or otherwise terminate the program, but with a signal, usually with a signal. And then that causes graceful stop or immediate stop, depending on what kind of signal was involved. That caused one of these two methods to be called on the listener. So a lot of this is stuff that pretty much all programs do, but it's part of it's usually part of libraries or conventions, whereas this is built into Ballerina, which means that when you're creating a small program, a lot of ceremony that you have to go through with other languages just gets handled automatically for you by Ballerina, which is quite a nice win when you are dealing with smaller programs. As I said, modules have a module can have an init function, and just as we saw in the previous talk, that objects can have an init function, and objects and modules are actually pretty similar. And so modules have an init function too, and this gets called after all the variables have been initialized in the module. And it can return an error, just like main can return an error. And so in fact, main, although we say there's a main, in fact, it's really you can think of main as being as having a little module that's created automatically that has an init that calls main. So really all there is in Ballerina is modules that get initialized and start and then stop. Okay, so we talked about module. In order to understand service, so we talked about listeners, we talked about module initialization. We now need to talk about service objects. So we talked about in part one, we talked about creating objects with class declarations. But there's actually another way you can create objects, which is you have an expression which just creates the object. No class involved here. This is called an object constructor, and it's an expression. And the result of evaluating the expression is an object. So this is an object which has one method called greet, which returns a string, and the string returns hello world. So you can create an object without, there's no class involved here. It's just an object. And we can use this pattern for creating services. So a service declaration is actually sugar, and we'll see how it desugars in the next slide. But what it does is it evaluates an expression to create a listener. So here we are creating a listener object. That will then register the listener, if necessary, with the module. We're then creating a service object. So this here is the body of a constructor for a service object. We are describing a remote function on the service object, and this remote function is which remote functions we need are determined by the type of the listener. So the UDP listener expects to get a service object with an onDatagram method. So we're defining an onDatagram method, and which takes a datagram, and we're printing out the length of the datagram. And that's it. And what that desugars to. So let me talk a little bit about responses. So many protocols use a request response pattern. When you use a client, the way it works is that if your call to our client remote method is making a request, then the return value of the call to that method is the response. And similarly, when you are invoking a service remote method that handles the request, then you can use the return value to provide the response. This approach has some limitations. The application doesn't get control over what happens if there's an error sending the response, and it only supports sending exactly one response to the request. So we support another approach too, which is that the service remote method gets a parameter that's a client object representing the caller, and the service remote method provides a response by making a remote call on this client object. So you have the simple way with a return value which handles, the 90% case, but you also have a more flexible way if you need it. So we talked about remote methods. For service objects, we have another concept called resources, and resources are used to expose services in a more RESTful way, whereas remote methods expose things in a more procedural way. When you have a method, it's typically named by a verb, do something or get this, or it's a verb, it's an action. Whereas if you think about nice HTTP interfaces, typically your URLs are not verbs. Where if there's a verb, usually there's something wrong. They're usually named by nouns, and you do get or put or post on these things that are named by nouns. So in order to support that approach, we have this concept of a resource, which is a more data-oriented approach to providing an interface to a service, exposing a service. It's motivated by HTTP, but it's not HTTP specific, and in fact, it's general enough to work with GraphQL. So in a resource method, the code you write, so here's the example here, the code you write, you have two parts to name your method, just like in an HTTP request line. First of all, you have the accessor, in this case it's get, and then you have the resource, which is hello in this case. And I don't know if anybody knows a modern JavaScript, but that actually looks just like an object getter in JavaScript. And it's you can think of this as being a generalization of object getter setter for a network environment. So the get, which verbs make sense here? depend on your protocol. They're not application specific, they're protocol specific. So the things that make sense for HTTP are the things that HTTP defines, get, put, post, etc. The function parameters for HTTP then naturally come from query parameters. So this would map onto a GET request to a resource /hello with a query parameter called name. So resources are hierarchical. So our concept of resource is that you have a path which consists of multiple segments. Your base path, which is what goes here, is an absolute. You can think of it as being an absolute path. The path that goes here is a relative path, and you combine the absolute path and the relative path to get the path that path of the resource. And one single listener can have multiple services. So if you have an HTTP listener, you can have one service at demo 1 and another service at demo 2. So each listener can have multiple services with different paths. And you can actually often in HTTP, what you want to do is you want to treat one of the paths as being a parameter. It's not fixed by the application, but it's determined by the application, by the user, by the caller. So in this case, I could, if I supporting a URL path of demo/greeting, and this segment here is actually treated as a parameter, and I can do that by putting the parameter here, and this then gets treated. If you put this like here in square brackets, then that gets treated similarly to a parameter specified in parentheses, but it comes from the segment, the path segment. So if I called this ID get /demo greeting James, then this would be called with name being bound to James, and so it will return hello James. So you can also have, so there are two ways where you can handle hierarchy. You can have hierarchical names here, but you can also have a tree. You can think of having a tree of service objects. You can have a hierarchy of service objects. Let me read what I've written down since I wrote that carefully. So the path of the resource method becomes the base path of the service object. So it's kind of like mount. If you know Unix, it's kind of like mount in Unix. And in fact, the root service, we saw earlier that the root service we could have demo 1, demo 2 with different service objects. And actually, you can think of that as being a root service that dispatches to, based on the path, dispatches to subservices. And this is what makes GraphQL work with services. With GraphQL, what you have is a graph of objects, and each GraphQL object, in the general case, each GraphQL object is represented by a service object, and what are called fields in GraphQL become become resources in Ballerina. Okay, so that's overview of providing and consuming services. Now I want to start talking about. Okay, let's talk a bit about data. So the concept here is what you might call plain data. So it's data that is independent of code that's operating on the data. So when you're having network interfaces, you really want those to be based on plain data. You don't want to send code between your programs over the cloud. And this is really the opposite. It's the opposite of object-oriented. In objects, what you're doing is combining data and code into one thing. And that's great in some cases, but it's the opposite of what you want to do when you are writing network interfaces. You want to have network interfaces not be object-oriented. You want them to be, you want to send data around. So a really important concept in Ballerina is this concept of plain data. And once you've got plain data, you can do, there's a bunch of things you can do on it. You can copy it deeply. You can do equality on it. And you can do serialization and deserialization without coupling. If you want it, you can serialize and deserialize objects, but you can't serialize arbitrary objects without some coupling between the two sides that are changing. You have to, well, either you send code, in which case you've got a trust problem, or you actually have to know about the classes involved. Both sides have to agree in advance on the classes that you're sending. One of the things we're trying to do with Ballerina is to make it easier to write programs that work on plain data. So I described in part one, I said that all Ballerina values belong to exactly one basic type. So the universe of values is divided into basic types, and we've got 4 kinds of basic types: simple, sequence, structural, and behavioral. So simple types, they're always plain data. We've seen 4 of them: nil, boolean, int, and float. And there's one more, which we will see in a minute: decimal. Sequence types are always plain data, and we've seen one of them so far, which is a string. And we'll see a bit later another one called XML. Then we've got structural types, and the thing about them, from a structural type, structures can contain anything, and a structural type is plain data if the members of the structure are plain data. So we've seen array. We haven't seen a tuple yet, but arrays, we have arrays and tuples, just as we have maps and records. We've seen those. And there's one more we haven't seen at all yet, which is table. And we'll see that a bit later. And then we've got behavioral, what we call behavioral basic types. And the thing about the important point, well, the sense in which they are behavioral is that they are not plain data. And we have functions, we have objects, we have errors, and with 3 we haven't seen yet. We have streams, and types, type desk type, which represent types, and handles. So let's look at simple type, which is plain data, which you haven't seen yet, which is called decimal. It works very similar to int and float. It's a pair. There's no implicit conversions. And the point about decimal is that it can represent decimal numbers, decimal fractions exactly. And this is good because float is IEEE binary float, and it has a lot of surprises which can trap the unwary. For example, if you try this little program, it will not print what you would think it would print, which is 100.09. It will actually print this. You can go and try that with Ballerina or other programs that use floats, and it doesn't work as you expect. It doesn't work reliably for processing decimal data, and the world runs on decimal data. That is, people write things in decimal, and they expect decimals to work like they expect your $10,000 computer to get things as right as your $5 hand calculator, and they don't. So the decimal type it's not as efficient as it's much slower than a floating point, because binary floating point is built into computer hardware, whereas decimals aren't. But often that doesn't matter. It's better to get the right result a little bit slower than the wrong result very quick. Another important point about decimal is that it preserves precision. In human terms, saying something weighs 2.1 kilograms does not mean the same as saying it weighs 2.10 kilograms. Precision has semantic significance, and binary floating point doesn't remember that, whereas decimal type does. So it's a separate basic type. It counts as any data. It works basically exactly. You have the same kind of arithmetic operations that you have with int and float. If you want to write a decimal number, you put D after it. D for decimal. For floats, you can put F after it. But if you don't put anything, it'll be assumed to be float. It's not infinite precision, it's a floating point number, but it's decimal floating point rather than binary floating point. It has 34 decimal digits, so that's enough. It's 34 decimal digits. I did a little sum. US national debt in cents is only 22 digits. The age of the universe in nanoseconds is 27 digits. So you're not gonna have a problem in using this to represent big things. And it's designed for it's designed to be. I hear that somebody's got some background noise. Okay. And it's designed to be a number that works not weirdly. So we don't have the more sophisticated IEEE features. It uses the person who's most responsible, most well known for the decimal type is Mike Kalishaw, and he designed it for a language called Rex. And there's a subset of the full IEEE decimal, which avoids the complicated stuff, things like infinity, nan, positive versus negative zero. So this is numbers like you. This is numbers like you learned in primary school. Basically, it's gonna work in a non-weird, non-surprising way. That's the idea. So we've got two more plain data basic types that we haven't talked about. We've got table. I'm going to go into these in more detail, but just to understand the big picture, I want to explain a little bit about these two basic types. So table, it's designed to work in a very similar way to array and map. A table contains records. And the key point about table, the way table differs from an array of records, is that it provides random access based on keys. So it's very like primary keys in relational database. And those keys are stored in fields of the records, or usually one field, but they can be spread out in multiple fields. And those fields the fields containing the key obviously have to be immutable so that the table can maintain the invariant that each field is uniquely identified by its primary keys. And then we have the Xml type, which is similar. You can think of it as a generalization of strings. It's a sequence type. It uses sequences in a similar sense to xquery. We have elements, we have text, process instructions, comments. Attributes are not XML, part of the XML type. XML attributes are represented by maps. And the language supports writing XML using XML syntax. Again, both tables and XML is quite a lot of detail, so we'll discuss them in detail a bit later on. Another key point about any data or plain data is that it can be made immutable. Any data value can be made immutable. You can't do that for objects because objects combine code, and code may expect the object to be mutable. So simple values and string values are inherently immutable. You can't make them mutable. But a structure of values, so an array, a map, or a table, you can make it either as mutable or immutable. So you can think of it as having a little flag on it that says, is it mutable or not? And that flag is fixed when you construct the value. And if you try to mutate something that's immutable, you will get a runtime error. And another really important point about immutability that is different from most languages is that our immutability is deep. So if you've got an immutable structure, that can only contain immutable structures, and that in turn can only contain immutable. You can't get from something immutable to something mutable. And that means that if you have a value that is known to be mutable, you can pass it around to other threads, strands, and it's safe for concurrent access. So our immutability is designed to help with concurrency. So we have a type. We have a type for any data, which is a plain data, which is called any data. And it's a subtype. So remember last time we saw the any type, which is basically anything except error. any data type is a subtype of any data that allows anything that is plain data. And once you've got something that's any data, then you can do, there are certain operations that you can do on it. You can do equals equals and not equals on something that's any data. You can make a copy of it using clone. You can make an immutable copy of it using clone read only. So in this Ballerina syntax, we use read only instead of saying immutable, which is a bit of a sort of computer sciencey kind of word. We use read only to mean immutable in Ballerina syntax. And one important point about clone is that clone doesn't copy something that's already immutable. If it's already immutable, it doesn't copy it. And the point about that is that clone is designed to make something safe for use concurrently. So if you've got something, you don't know if it's mutable, you can clone it and you'll have something that you can is safe to use concurrently. You can also, so const, remember we saw const earlier, we had const, constant integers and decimals. In fact, you can have any kind of any data can be const. When you do clone read only, it's possible to so no, let me start again. So you can have cycles in your because we have assignment. You can have structures that have cycles in them, and equality can therefore get something with cycles in. So equality knows about that and can deal with it, and not, I hope, well, the spec deals with it. Pretty sure the implementation does too. So we deal with cycles both in equality and cloning. And another final thing that you can do with something that's any data is you can have it be configurable. So often a lot of application code is just allowing users to configure various things in config files, and there's a lot of repetitive code you end up writing in most applications to allow people to specify things you need to be configurable, that need to be configurable. And in Ballerina, it's very simple. You just put the word configurable in front of the variable, and we have a whole system that takes care of that for you. And that works for anything that's any data. Okay, so the next thing I want to talk about is data typing. A key feature of Ballerina is that data types don't just describe data that you have in memory that you're working on in your program, but they also support data that is being used, data on the wire that is being sent between services. And this is really crucial for the cloud era, because if you remember the going back to the diagram with going back to this here, APIs in the pre-cloud era used libraries. So you can have the libraries are defined by function types. Functions can pass objects around. So you can just use, your data types don't have to deal with, you can describe APIs just using regular data types, which include objects or anything you like, because you're not crossing process boundaries. But in the cloud era, it's very different. In a normal programming language, you have a problem, because you have your typing system for your language, your data type system for your language, that describes the types of function calls, it describes the types of variables that your program operates on. And then you have a completely different thing for describing how your program talks to other programs. And that's just a terrible way to do things, because you don't want to have describe your interfaces twice. You want to, the main point of one of the main points of a programming language is you use types. You want to be able to use types to describe your interfaces. And the interfaces that are important in the cloud are network interfaces. So you want to be able to use your type system, not just to help you catch errors in your program, but to describe the interfaces of your program. But when you start to do that, you need something that's a little bit different from the kind of a type system that you have in a regular programming language. You want something that's a little bit more like has some of the same flexibility that a schema language has. And Ballerina's type system has that. And so I'm going to show you some of those features. So one simple feature here is that you can say that a field is optional. So this is a record and it has a from field and a to field and a subject field, but you don't have to have the subject field. Now, that's an absolutely basic thing that you want to be able to express. If you're thinking of this as being a wire format, you might think of this as being a JSON on the wire. You want to say, okay, I can have from, I can have to, and I may or may not have subject. That's a very simple thing, but it's kind of basic. And if you want to use your type system to describe network interfaces, you need it. If you're actually going to use this in the language, not only do you need to be able to describe public fields, you need a way to access these fields. And so we also have a syntax that accesses an optional field, and that will give you nil if the field is not there. That syntax there. We also have another concept that's really important when you're dealing with network interfaces is extensibility. And our record types are what we call open by default. That means they allow fields other than those specified. So if I have a person type, which I write like this actually means that it must have a name field called string, and it may have other stuff, and we don't care about that. And the other stuff and by default, the type that we don't, the fields that we don't specify, we require that their type be any data. So if you have a record like this, it is any data, but we don't say what the other fields are. So what this means actually is that records, so previously up to now I've been talking about records and maps as being two different things. They are actually the same thing. Records and maps are just two types you can write to describe one thing, which is basically a mapping. And any open record here, and it's an open record like that, belongs to map any data. So a map whose fields are any data. So let's have an example here. So we've had a person, which is an open record with a name. So this means implicitly that you can have other fields of type any data. And so here we have a person P2 with a name, and we've added another field, country, UK. We put that in double quotes because we require that to be in double quotes, in fact, just to help with avoiding typos. Otherwise, if you have option, if name was optional, it's otherwise anyway, it helps you to avoid errors to require these unmentioned things to be quite double quoted like this. And that is just actually a map. That is a map. Not only is it a instance of a person, but it also is a map whose fields have type any data. Is that clear? Good.
So does that mean the underlying representation of a record is a map?
You could do it like that. I mean, an intelligent implementation is going to optimize things, but there are lots of implementation possibilities. But in a naive implementation, yes. In a naive implementation, an implementation of an open record would just be a map.
Okay.
You can actually, so we don't force your records to be open. We can control it. So if you want a record that isn't open, that just allows what you said, you call it a closed record, or exclusively allows exclusively what's listed here. We use this separate kind of delimiter. Instead of using curly braces, we use curly brace with our bar there to indicate, and that means that it's closed. And we can then actually control, we can actually explicitly say, well, what kind of, it's open, what is it open to? And you can control by using this ... syntax. So this means here that you have headers, we have a from header, we have a to header, and we have other headers, and we don't know what their names are, but their values are always a string. So when you actually have something without an open record, without the bar, that actually means implicitly any data ... And so map is actually, map T is actually the same as a record, which just allows any records of type T. So maps and records are completely unified, and in fact that they're just two different types for describing the same universe of values. And this is what you want. Why do you want to do this? Well, because we want to work with JSON. One big reason is we want to work with JSON, and JSON only has one kind of thing. And in JSON, you use objects to represent both maps, which is where you don't know what the keys are, and records, where you actually, the application is specifying specifically what the keys are. Okay, now we can talk a little bit about JSON. So the JSON type is actually is a union, and it's a union of the simple types and string and array of JSON and map of JSON. And obviously, if you have a value of this type, you can convert it very straightforwardly to and from JSON, except for numbers. So I'll talk about how we deal with numbers in a bit. But apart from that, because there's a very straightforward mapping between JSON and on the wire JSON format. And also notice that Ballerina syntax is JSON. When you write, you can actually put JSON in here, and that is Ballerina. That's valid Ballerina. We actually, in order to make this work, we also allow null in order to make it the case that you can take JSON and stick it in, and that's valid Ballerina. We also allow null to be written for nil. But we generally prefer people to write, because our concept of null is very different from the JavaScript concept of null. We encourage you to use the nil syntax instead of null. So JSON, how does JSON write any data? JSON is basically any data, but without table and XML. But you can convert any data to JSON very straightforwardly, and there's a toJSON Lang library method that will do it. Table values are created to arrays. So your table table contains maps, and you just convert that to the corresponding array, and XML values get converted to strings with the XML representation of the XML. So note that JSON and XML are not parallel at all. XML is its own separate world, whereas JSON is just a union. It's just basically a subset of any data. Plain data and JSON are very, very similar. Any data is just basically JSON ++, whereas XML is its own separate world, and that reflects that XML has an idiosyncratic approach to representing structured data, and you need to work to turn that into something that is convenient to work with in memory. Although you can, anyway, I'll sort of talk more about XML later. So if working with JSON as well, JSON is the lingua franca of network services, and there are two basic approaches to working with JSON. Approach one is you work with JSON directly. And approach two is that you write a type that's a subtype of any data. You write your own application types to represent what your application is working with, and then you convert from JSON to these types, and you work. Your application logic is written in terms of these types, and you convert to and from JSON when you receive it or send it. You can do both in Ballerina. We support both in Ballerina. Where Ballerina shines is that approach 2 is really hard work in other languages, but it's actually quite easy in JSON because our types and our concept of plain data is very similar to JSON, and because of our type system. But let me talk about approach 1 first, because sometimes you don't want to. Sometimes you don't really want to go to the effort of writing a type and converting them. It's not a lot of effort, and generally I'd recommend, whenever you can, just write a type. You don't have to write. Your type doesn't have to be. It can be a fairly loose type. You can just describe the bits that you're interested in and leave the rest as JSON. But if you don't want to write the types, you can work with JSON directly. And we have a concept called lax typing, which is a little bit like dynamic in C#, if anybody knows that. And the basic concept here is that when you're working with JSON directly, typically you are not dealing with arbitrary JSON. You're not trying to write programs that deal with any JSON, any possible JSON. What you're trying to, you have in your mind, you have implicit a particular schema, a particular JSON schema that you are expecting. And your program is only going to work with, is only intended to work with JSON that matches that particular schema. So we want to make that convenient. And so we have a slightly looser approach. So really there's an implicit schema. You want a more dynamic approach. And the basic idea here is that instead of things being compile time errors, we make them runtime errors. So usually if it wasn't JSON, you can't say .x, .y, .z unless you've got a type that, unless you've defined a type for J that has an X field, and you define a type for X that has a Y field, and so on. So you usually want that kind of strong tagging. But if you decided that you want to work with JSON directly, you decided you don't want that. So instead we say, okay, well, we'll let you do that. And if you don't have if it doesn't have that field, you're saying basically at runtime, I'm expecting that this is going to have an X field, this is going to have a Y field, this is going to have a Z field. And if it doesn't, then that's not what I'm expecting, and I want it to be an error. So the concept is that this will evaluate to an error, which you can then catch with check. And similarly, that if you're saying here you're converting it to a string, that means you're expecting this to be a string, and again this will check at error. So there's a little bit of magic here to when you are using JSON. There's a little bit of magic that works more like a dynamic language, and will it still fits in with Ballerina's philosophy that errors are represented by error values and not by exceptions. But it makes it less painful. Otherwise, if you didn't have this, it gets very painful. You have to use square bracket. It gets just more verbose. You have to use square brackets. You have to put the thing in quotes. You have to check for nil all the time, and it just gets to be a pain. So we have some convenience here to make it easier if you don't want to write types. Okay, so another way that you have this feature that you can use to work with JSON. You can also use match. You can also use match statements. So your match statements can have basically patterns in them that can match fragments of the tree that you're working in. So here we're saying we want to match a record that has a command with a value of add and has an amount field, and then we want to bind the value of the amount field to X. So doing this, you can actually pick apart JSON, complex JSON hierarchies, and see whether it matches what you want and pick those out. It wouldn't. There's no concept of, there's no pattern at the moment that searches at arbitrary depth for something. But if you expect it to have a structure, a specific kind of structure, then you can match on that structure and pick bits out of it and do what you want with it. So this means, to be clear, that it has this semantic here is open. So it means you have this field and you have this field, and you may have other fields, you don't care about those. So that's one way to deal with JSON. The other way to deal with JSON is to convert from JSON. So you need to do it both ways. You need to go from user-defined type to JSON and vice versa. Going from the user-defined type to JSON is very straightforward, because our user-defined plain data types are JSON. So there's nothing to do. If you've got a subtype of, so this, in this case here, we have a closed type, we've got two floats, we've got a value here. It is JSON, there's no conversion required, it just is. Nothing to do. If you had a open record type, then there's the complication, because records are open to any data, and any data, JSON is a subtype of any data, and not vice versa. So that means there's a possibility here that you could have things that are not JSON as other fields, and you can deal with that by doing to JSON. That will convert tables to arrays and XML to strings. So you can convert this user-defined open type to JSON using to JSON straightforwardly. So going from user-defined type to JSON is pretty straightforward. Well, it's straightforward because of the way we set things up. Converting from JSON to a user-defined type is more interesting. You can't just use a cast. You might think you could. You might think here, well, okay, so I got this JSON value, I got this type. All I've got to do is cast this value to this type. But that doesn't work, because it would not be type safe. If this was allowed to work, suppose this worked, J still points to this, so I could then do J.x equals, I could assign J.x to something wasn't a float, and boom, it wouldn't work anymore. So we can't allow that to work. You've got two ways you can do it. You can make it, so this is to do with inherent types, which we talked about when we were talking about covariance in part 1. So you can make it read-only. In that case, you can just do clone read-any. If you've got a read-any copy, you haven't got to worry about inherent types. Structural typing works straightforwardly. You can do it like that. There's another way you can do it, which is called clone with type, which is a very important feature of Ballerina, and is what makes data binding, what makes Ballerina really convenient to work with when with network interfaces. So what this does is it clones J, but it uses the inherent type it gets from coord, and in fact you don't need even to put that in. It can get that argument. So this is a type desk value, which is defaulted from the context. So what this does is it constructs you can think of this as constructing a coord value using this as the data. So it's doing a copy. The copy will be equals equals, but it will have the right type too. So this is what when you are doing this is what happens when you're using this in conjunction with services. This all happens automatically. So let me give you an example here. Suppose we're writing a calculator service, and we're going to post we're going to post things to it in order to get things done. So we've got a record here with two decimal arguments, X and Y, we're going to call them. And you can, so we've got an annotation here, which tells us that the arguments are going to come from the payload rather than from, without that, they're going to be treated as being a query parameter. So we want to say, okay, these args come from, this data here comes from the payload. And so what the listener is going to do when it gets this, when it sees /calc, it's going to look up the, and it sees a poster /calc/add, it will look up the, it'll use the post accessor, it will use the calc/add resource, and then it will see that, okay, I've got, what do I do to the, where do I get this from? I get this from the payload. I'm going to expect the payload to be in JSON. That's what's by default. And then I'm going to do basically clone with, I'm going to take the JSON on the wire. I'm going to convert it to a JSON object. That is a lowercase, a Ballerina JSON value. And then I'm going to do clone with type with the type args. And so I will get, without having to do anything, I will automatically get a nice args value that has the right type. And I can just, I don't have to, I can now work with this conveniently. I don't have to, there's no checking involved. All the checking's been done for me. I now have got the right kind of thing. I can just add it up and return it. And then this decimal is a subtype of JSON, and it will then get converted back into JSON. So all the data binding, the conversion to and from between the wire format, the JSON wire format, and my types is dealt with automatically by the system. And also from, so I write the types once, and from this type that I've written, this Ballerina code, I can then go generate an open API description that will enable a client to use this in a strongly typed way. So this is what I mean by we're using Ballerina types to describe the data on the wire. We're describing Ballerina types to describe network interfaces. So I have one thing I haven't explained yet. I said, so I remember if we were talking about conversion between Ballerina and JSON, it's all simple except for numbers. So let me just explain how numbers work, because numbers are important. Basic problem is we've got three numeric types. We've got int, float, decimal, and JSON has one. So the JSON Ballerina type, which is a union, allows any of them. So again, going from Ballerina into JSON syntax is straightforward. Each of these types can be converted into JSON numeric syntax. The other way around is more complicated. So what we do is we first of all, what we want to do is to be able to handle all the types and not lose information. So the way we do that is basically it's two stages. First of all, if you don't have any type information, then when you parse JSON, what you will get is things that are integers in the JSON syntax and they fit in our 64-bit ints, will be represented as ints. Otherwise, we will represent things as decimals, because decimal preserves because JSON uses decimal syntax to represent numbers, and so by using decimal, we can not lose information. So in the first stage, you convert things either into int or decimal, and you've exactly captured what is in the JSON. And then when you use either clone with type if you're using approach 2, or ensure type in approach 1, you can then convert from int or decimal into whatever type the user specified. And the net result is that it works basically. If you have a Ballerina program, if you're using JSON to represent decimal and you use decimal in Ballerina, it will work. If you're using float, it will work. There's one slightly difficult edge case, which is minus -0, because our decimal type doesn't have -0. So all values are represented. There's one value that's represented as float, which is -0. So that means that basically we deal with the full range of float, int, and decimal, and you can exchange them between Ballerina programs in JSON without loss of information. So I think that's probably going to be, that's 1 hour and a half. So I think that's a good place to stop.